Okay, so now we're going to take a look at one of the other more common equations that people know from modern physics, brought to us by Einstein. E equals mc squared. Well, it's something that has been talked about time and time again in popular culture and in, honestly, day-to-day life. Very few people have actually had to apply it in anything resembling a quantitative way. That's one of the things that we're going to do now. And from this, we're going to see the massive amount of energy that is stored up in just the mass of an object. We found that energy, or mass I should say, is nothing more than another form of energy bound up in what we deal with on a regular basis, something physical. And if we could convert that into pure energy, then we would end up with quite a bit of it. Now this originally comes from radioactive materials, things like radium, which the Curies explored, and uranium, among other things. And this is also how we can get something so powerful as nuclear weapons, or even the power of the stars themselves that keep life as we know it going on this planet. It's because very small amounts of mass, can be converted into large, large quantities of energy. And today, what we're going to take a look at is we're going to do a bit of a comparison. We know that there are many different ways to get energy out of things, and while this is one of the most energetic ways, for the most part it becomes very difficult to release all of the rest mass energy of a material. You'd need a whole lot of antimatter in order to do that. But let's get an idea. So what I want to know is, the other day I had a burger, and I'm going to say that it was probably about, total with the bun and all of that, its total weight, its total mass was probably about half pound. So it's going to be pretty close, at least in the ballpark, of 1/4 of a kilogram. It's just doing some rough estimates in my head here. But the mass of this burger would be something like 0.25 kilograms, at least pretty close to that. Okay, and I'd like to know, now my body, as most people's bodies do, unless of course they're holograms, so I'll leave that to your particular decision, but normal people, when they eat food, it will metabolize the food and they'll break them down, breaking down chemical bonds and moving the chemicals around and getting energy to be released from that. We understand that now with things like Coulomb's law and the energies associated with that, because we can get charged particles. The closer we get them together, they'll have different energies, and so we can get some energy out of that. But what we're going to do is we're going to see how much energy we could get if our bodies could instead actually annihilate all of the mass of that burger and turn it directly into energy. Now, that would be impressive and mean that we could probably run for quite a while off of one lunch, but it would also probably mean that we would irradiate ourselves horribly. So, we'll see. But let's find out how much energy we end up with. Well, we've got our mass here. We're going to plug it into the ubiquitous E equals mc squared, so I'm going to go with 0.25 kilograms. And I'm going to multiply that by the speed of light squared, 3.0 times 10 to the 8th meters per second, quantity squared. When I do that, I end up with the following value. The energy stored up in the rest mass is what we call it, but basically the energy that's going into making all of that mass there is equal to 2.25 times 10 to the 16th joules. That's how much energy I have built up into that. Okay? Well, that's a large number. That sounds impressive. I know. Let's compare this to the actual energy that our bodies get from say, one of these burgers. Let's assume, although we're probably rounding down, that the burger has maybe 100 calories. Now, if you're familiar with this sort of thing, then you can probably follow along. If not, you don't have to worry about the next couple of steps because it's not something that I've included in the physics class that we're doing. But this is calories with a capital C, which is a little bit different from what we're used to with regular calories. And we would convert this by a factor of 1,000. So that gives me 100,000 little calories. And little calories are defined as the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. There are a number of different things in there that go into the exact definition. I don't remember it right offhand. It's really more of a chemistry thing. We deal with it in some of the physics classes, but not a whole lot. There's too much other stuff in thermal physics to deal with. But Doing the conversion, I should end up with something on the order of one burger, which is 100 big calories, something that we're used to, should end up with the equivalent energy of about 5.0 times 10 to the 5th joules. That gives us an idea of compared to how much energy we actually get out of the burger just from eating it and metabolizing it, moving around some of the atoms and getting some energy out of that. Now I can compare how many burgers I would have to eat to get the same amount of, if my body could just convert all of that matter, that mass, into energy. Okay, well, if I want to find out how many I would need to eat in order to get this much energy, well, that'd be nothing more than my number is going to be equal to the energy from the mass, from actually converting. This is my total energy that I want to get, and for every burger I eat, I would get this much, so that's this energy. And so I'd find out how many of them I need to give me the total energy by setting up this ratio, which that's going to be 5.0 times 10 to the 5th joules divided, or that quantity is dividing 2.25 e to the 16th joules. Let's find out how many burgers I have to eat to get that same amount of energy. The number that I get, ready for it, 4.5 times 10 to the 10th burgers. In other words, I would have to eat 45 billion burgers to get the same amount of energy that I could get if I could somehow simply change all of that mass into energy. Now this is a ridiculous, ridiculous amount of energy. And this is one of the reasons why nuclear weapons, they can take a very small amount of matter, mass, and they can turn it into an extraordinary amount of energy. And this is what Einstein gave us, and one of the reasons why this is such an impressive equation. Most people who mention it, they mention it on some sort of metric of, hey, it's a smart thing to say. But very few people have actually looked back into it to see what it actually says. And it says that for all of the things we encounter on a regular basis, a calculator, a remote, a book, for all of this mass, it's nothing more than an incredible amount of energy which is somehow stored up in this mass. And we can move from one to the other. We can either move energy into mass or mass into energy, depending on exactly what processes we're using. Now, there are a lot more limitations onto exactly what we can do, and we're still exploring even the basics of this. Right now, with all of the energy involved in it, we can't control it. And that's why the only things that we've been able to do are to make bombs, things that release all of this energy at once. But let's not lose track of the fact that this much energy can also be something good. This sort of reaction happens inside the sun every second. In fact, much more energy than this. And it is the cause of all life, all energy as we know it here on the Earth, with the exception of some fissile material, etc., etc. But we could discuss that quite a bit more. In the end, this relationship is responsible for all of the energy that we're dealing with inside the universe right now. And it's keeping track of one form or another, mass, energy. And we can see that there's a lot more built up into it than we can easily imagine. 45 billion burgers.